Intro piece, we have a circle, right? I can use my fancy circle making tool. All right, we have a circle, and every circle has a center. So this would be the center of our circle. We can call it C. Right. All of these, everything in this red line, we consider a point. Think of it as a bunch of points super close together that make this shape. Right. And we could take the distance from the center to any point on the outside. So let's say I want to find, we're on a graph, so let's say I want to find this point, and it's the point x comma y. Okay. Well, to find the distance between those 2 points, you would try to find the shortest path possible, which would just be a straight line. So the distance, well, the point I'm getting at why I'm showing this picture, the distance between the center and any point on the circle is just, well, we know that going to the center of the side of the circle, this is a radius. This is our R value. All right. If we were to draw, let's say we're going to figure out another point on the circle. Let's say we have one over here. Well, that point, we're going to find the distance between these two. It would be the shortest path possible. Here to here, well, we just made another radius. We're going to go through today and use a process using our distance formula and the fact that the radius is the same thing as the distance from your center to any point on the circle, and see if I was to give you any random point, could you determine whether or not it would actually be on the circle? So with that, we're proving or disproving the following statements. So we're either going to have false or true at the end. The point, square root of 2, square root of 2, lies on a circle that's centered at the origin. And we're just going to start with that part. I'm going to put another circle up on there so we can have a visual. Oh, nope, that's a rectangle. I want the circle. So we have our center right here. And we have a point on the outside, 2 comma square root of 2, square root of 2. We could say square root of 2 comma square root of 2. That's just a point on the outside. We know that point is for sure on the outside. And we could figure out what our radius would be. Here's the part we're going to prove or disprove. We're going to say, well, what if we have the point 2 comma 0? We don't know if that's actually on our circle or not. So that's why I'm going to put a question mark here. That's what we're trying to figure out. Is this point a part of this circle? To figure out whether it is a part of the circle, the distance from the center to square root of 2 has to be the same from the center to 2 comma 0. We're checking to see that both of these have length R. So first, we're going to use R, so we got to figure out what R is. We're going to take the distance from this point from the origin of our circle, which is our center. The origin is a specific point. It's the point 0 comma 0 is your origin. It's the dead center of your graph. So how I like to write this is saying, well, we're really trying to find the radius, but our radius in this case is the same thing as our distance between point A and point B. And we can use our distance formula that we worked with at the very beginning of the year, where here's your formula. I'll give it to you again. It's x subscript 2 minus x1, we call it, squared, plus y2 minus y1 squared. So I'm going to label this point here my center. Oop, I'll zoom out, sorry. I'm just going to label my center as 0, 0 as well before we start. So first we're going to figure out the distance between here and here to establish what our radius is. Because we know this point for sure is on the circle. So I could go through and label these as, let's say this is going to be my x2 and my y2. And this is going to be my x1 and my y1. Using those, I can plug them into my formula and figure out the distance. Doesn't matter which one is x1 and y1 and which one's x2 and y2 between the 2 points. It always has to be x and y. I like to do, if I have a 0, I make that my x1 and y1 because then I'm always going to be subtracting by 0, which does nothing. All right, so let's work on this now, plugging in our values. Again, this is going to be like an algebra heavy order of operations type stuff, where we take the square root of 2 minus 0 squared plus, again, we have the square root of 2 minus 0 squared. You could do this all at once if you were to plug it into your calculator just like this, like your parentheses squared. It would shoot out the number for you. But we'll just take it step by step so you can see us going through it slowly. So square root of 2 minus 0, that's just a square root of 2. So we have the square root of 2 squared plus, same thing on the other side, square root of 2 squared. I'll zoom in more if I can. Squaring a square root undoes the operation. So we would be left with the square root of 2 plus 2, which then is equal to 2 plus 2 is 4. Square root of 4, which square root of 4 is a perfect square, so we can take out and we get a whole number. So we get 2. That's our kind of our halfway answer, because again, like I said at the beginning, we're just saying our final answer really is a yes or a no or a true or a false. So this is our radius or our distance between the 2 points on the circle. So I can go back into my diagram and label this as our radius is equal to 2. So now what we're going to try to figure out is this radius or is this distance between these points, does it equal 2 as well? And to do that, we do the distance formula again, but instead we're finding the distance between 2, 0 and x1, y1. So doing this again, we could use these as another point. This could be our new x2 and our new y2. And we do the distance formula again. So I'll draw kind of a dividing line so we know we're doing it 2 different times. Our radius now, or our distance, is equal to, I'm not going to write the whole thing out, I'm just going to plug things in right away. x2 minus x1, that's 2 minus 0 squared, plus our y2 minus our y1, which is 0 minus 0. So we'd have 0 minus 0 squared. Going through, doing some simplification. This will be square root of 2 squared plus 0 squared. So then we would get out, again, you have to, when you're going through these, you'll probably show less steps. This is 4 plus 0, so this is the square root of 4, which is then equal to 2. So what we just showed is that the distance between 2, 0 in our origin is equal to 2 as well. So this would be a true statement that 2, 0 is on, we could say, the circle. Why it's on the circle? Because we know we start off with this definition of a circle that any point on the circle is equidistant from the center. Everything around here, any point that we draw, the distance between the origin and on the outside should be 2. In this case it is, so we know it's on the circle. So really, you're doing the distance formula twice. First to find your radius. Second time to figure out if your other 2 points have that same radius. So we'll do that again with the second example. If you want to try to work ahead and do it on your own, I would encourage that because it'd be good practice. Otherwise, just keep following along. I'm going to put in another circle in there because I like the visual. Hope it's a green circle now, so that's cool. It's kind of more ovally shaped. Let me make a different one. Actually, don't know how to. Can I just erase it all together? I'll make a better one. There we go. All right. So again, we're centered at the origin. So we're centered at 0, 0. We can make that our center. 0, 0. And we have the point 3, square root of 7 lies on the circle. We know that's our thing that is true. That's not what we're checking. We know it to be true already. So that would be, you could say right here, 3, square root of 7. Again, like I just said, the first time using the distance formula, you have to find what your radius is. So we make it easy on ourselves and we label our x and y points. x2 and y2, x1 and y1. That just makes it easier plugging things in. You don't have to kind of track where everything is. You can just plug in and go from there. So here's our distance formula the first time finding our radius. So your radius is equal to x2 minus x1, so that's 3 minus 0 squared, plus square root of 7 minus 0 squared. So this is kind of where it's nice if you're at the origin, your x1 and your y1 0, because then just subtracting off 0. And then showing this step isn't always necessary because we know it's just going to be the same. So simplifying, this would be 3 squared. This would be square root of 7 squared. So you'd get the square root of 9 plus 7. Combine underneath, so you get to one number that you can take the square root of. Square root of 16, which is equal to 4. So we know for sure that our radius is 4. Now we're verifying that the point 1, 4 is on the circle. That's what the question we're asking ourselves. For it to be on the circle, the distance between these 2 points has to be 4 as well. So again, we're going to do the distance formula a second time. Here's our x2, here's our y2. Our new x2 and y2. I'll draw a dividing line to show that this is kind of a new distance formula. It's be equal to, it would be 1 minus 0 squared plus 4 minus 0 squared. So you'd have 1 squared plus 4 squared. Which would be 1 plus 16 is equal to the square root of 17. Which I already know it's not going to be 4. We want to be exact. Square root of 17 is about 4.12. So these two distances are not equal to each other. Even though they're close, they have to be exactly the same for it to be a circle on the circle. So how I would kind of show my answer, I like doing just saying that, well, 4 is not equal to 4.12. So this would be we would say this would be like false. False. It's close, but not exact. It's got to be exact. All right. Last piece. Talking about earthquakes and epicenters. This is we're really just drawing 3 circles right now. And really why I'm just showing this is because there's one on the homework that deals with phone towers that's similar. But once I do this, you'll get the idea. We have 3 earthquakes happening. We're trying to find where they all converge. We have earthquake A, B, and C. It gives us where the center of each earthquake is and how far it's like rippling out. So earthquake A, its epicenter is at -2, 2.5. So you want to draw a point there. So you go over 2, up 2.5. Over 2, up 2.5. And then if the epicenter is 7 miles away from the center, that means our radius is 7 in every direction. So you should draw a circle as a radius of 7, which is hard to do if you just eyeball it. So I just draw kind of the top and the bottom and the 2 sides and draw the best circle I can. So I count 7 to the side. 1, 2, 3, 4, 5, 6, 7. Count 7 above my epicenter. 1, 2, 3, 4, 5, 6, 7. It would be somewhere up here, I'm estimating. Count 7 to the side. 1, 2, 3, 4, 5, 6, 7. Somewhere over here. And down 7. 1, 2, 3, 4, 5, 6, 7. Somewhere down there. And maybe you're good enough where you could just go like all the way around. That'd actually be very impressive if you could do that. I just do 2 semicircles and try to get as close as I can. Big ideas when you have to do this. It's nice. It'll make it a perfect circle for you. But there you go. So that's earthquake A. Earthquake B, we're going to do the same thing. Find your epicenter. Make your radius 4. Draw your circle. So you have 4, 6. 1, 2, 3, 4. Up 6. 1, 2, 3, 4, 5, 6. We have to go 4 in every direction. 1, 2, 3, 4. 1, 2, 3, 4. Go down 4. 1, 2, 3, 4. Go up 4. 1, 2, 3, 4. Be somewhere up here. So we have that. That's earthquake B. And earthquake C, it has a radius of 5 miles. So we go 3, -2.5. So to count 5 in each direction. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then shh. Ooh, that was terrible. All right, something like that. And then what we're looking for is where kind of all 3 intersect. And since our graphs, we're doing this by hand, it's not going to be exact. But we'd say it's somewhere in this area is where they all converge. And you could kind of estimate where that point would be. It's like right here is kind of the closest that we got, this black point. So we could say they all converge. We count over. That's 1, 2, 3, 4. 1, 2, 3, 4. It's about 4, comma 2. You may have 5, comma 2 or 5, comma 2.5, depending how you have it. So even though like where they don't intersect, that would be an example of like, I don't know, you're somewhere but your neighbor had an earthquake but you do not. All right, you'd be in this part right here where the circles aren't overlapping each other at all. This is how like what you'll see in the phone tower example, like when you have a dead zone on when you're making calls. If you ever see like the commercials that are like, oh, we're T-Mobile, we have like the best phone plans, like look at all the coverage we have. What they do is they basically do this process. You don't have to write this down. This is just a kind of example of how they would make that graph. Where they say, okay, we have this graph. This is we could put America on here, and we have all these kind of hot spots. And then instead of leaving them as open circles, what you see on the commercials, I think of the T-Mobile one because it's all pink. They fill everything in. And then you may see they're like, oh, well, we have this one right here, but then if you live right there, you live in a dead zone. But if you live like in here, you may have better service because you have 2 phone towers coming at you. If you are, I don't know, you live in between, you're close to 2 other ones, but you're really only getting service from 1 phone tower. Kind of interesting, kind of a way that, I don't know, geometry applies to real life in a kind of simple way that affects your everyday life. So yeah, that was us wrapping up Unit 10. You got one more big ideas assignment from Unit 10 to do. It's 10.7D2. It's just, I think it's a few examples of like the proving or disproving. I think there's 2 word problems maybe, and then there's some review on just arc measurements. The keys posted. I think that's all I have to say. Sorry, we said we were due next week. Happy Friday.